Now we continue with our last speaker. It is Vladislav Kataev. Okay, the title of his talk is Interplay of Magnetism and Topological Electronic Structure
where's the pointer?
Magnetic van der Waals compounds. Vladislav Kataev is from Leibniz Institute of Solid State and Materials Research from Germany.
So good afternoon, everyone. So I'm Vladislav Kataev from the Leibniz Institute for Solid State and Material Research, EOW Dresden, which is situated in the eastern part of Germany. Well, and today I will introduce you in a relatively new field of research, which is focused on so-called magnetic van der Waals compounds with untrivial, let's say, topological electronic structure. So I will present some of our results, and all this project was done in a big collaboration of different groups within the Germany and also outside the Germany. So the nice single crystal, high quality single crystals were synthesized in the group of Anna Isaeva at the Technical University of Dresden. Extensive measurements of the band structure with the use of the angle resolved photo emission spectroscopy were done mainly at the University of Würzburg. And the main player, there were two guys, so Raphael Vidal and Henrik Bentman. There was a great input from the theory side, actually one from the San Sebastian, so from the group around Evgeny Chulkov and Mikhail Otrokov, who actually made a momentum, the first momentum to our research by predicting the first antiferromagnetic topological insulating material. And also, so our understanding was of the interplay between the magnetism and electronic structure would not be possible without the input of the theory group in our institute around Jeroen van den Brink, where the main player was Jorge Facio. So I will present quite a bit of magnetic measurements, and they were all done in our institute in Dresden. And my focus will be on the electron spin resonance spectroscopy results, and there the main player were Alexey Alfonsov and Kavita Melava. Very important was, of course, the funding. So this project was done in the big collaboration supported by the Deutsche Forschungsgemeinschaft. This is German Science Research Foundation, which financed an excellence cluster between Dresden and Würzburg called Complexity and Topology in Quantum Matter. So, it doesn't work anymore. No. Okay, so this is an outline of my talk. First, I will just give a short reminder for those who are not really involved in the topological insulator. So then also I will introduce, or just explain, the recent trend of combining magnetism and topology in these kind of materials. And then I will talk about the first antiferromagnetic topological insulator, where the magnetic units form a regular magnetic structure. So this is a family of manganese bismuth tellurides. And then I will give you some results of our electron spin resonance spectroscopic study, which helped us to understand the intrinsic ferromagnetism of the magnetic building units of these compounds, and also addressing the dynamics of the manganese electronic spins in the paramagnetic phase and possible interplay with the topological electronic structure. So, and finally, I will conclude. So now, actually, what is a topological insulator? What is distinct with, say, a conventional band insulator, which is known, for instance, very well in semiconductor physics? So the ordinary insulator, so it has a valence band and it has conduction band, as usual. And normally, the valence band has a p character, so it has an orbital momentum, and the conduction band does not, it's s character. However, if one switches strong spin-orbit coupling, which typically is the case in heavy metals, so then the order of these bands could change, meaning that, for instance, now the valence band has preferably the S character and the conduction band preferably P character. So this inversion of the bands, it can take place only in this material. That meaning that the interface either with vacuum or with conventional conventional insulator, where the spin-orbit coupling is absent or very weak, means so that this original order of the band should be restored, and inevitably, so this inverted band should cross on the surface. So that meaning so that in the bulk it is an insulator, but at the surface there should be conducting states. And this is visualized so that in this graph from the paper of Takura et al., where so these surface states, so they form this kind of Dirac cones with linear dispersion. So the momentum, the energy of this electron depends linearly on the momentum. And the specific of these surface states, which is very important for the physics, is that these states are spin polarized. So because they are protected by the time inversion symmetry. So that means that the electron, which has a positive momentum, it has a certain direction of spin, and because of the spin-orbit coupling, so this spin is locked to the momentum. That means if an electron travels in a certain direction, it has a spin up. And it can travel in the opposite direction when only it has a spin down. And that has important implication for the transport properties, because in this material, so for instance in the insulator, in the topological insulator, so there are these currents, spin polarized currents on all surfaces, protected by this time reversal symmetry. But that transport is, for this reason, is practically without dissipation. It's kind of ballistic transport. Because in order to be scattered, this electron, it should change the momentum, but this momentum implicitly would force the spin to flip. And this is not possible because it violates the time reversal symmetry. So a very interesting situation was well observed in several materials. Like, for instance, a very famous family of tetradiamides. So this is basically, so these compounds containing heavy metals with a strong spin-orbit coupling, bismuth selenide, bismuth telluride, antimony telluride, and so on, where indeed experimentally in the angle-resolved photoemission spectroscopy, so the evidence for the surface states linear dispersing in momentum were found. Now, so actually, so there's a very rich physics which was expected to happen in this material, and indeed it was realized. So in particular, so regarding anomalous quantum Hall effect. So if you remember, so there is a famous quantum Hall effect discovered by von Klinsling in 1980. So it is the situation in a two-dimensional electronic gas which is exposed to strong magnetic field. So with the absence of the field, so this two-dimensional electronic gas is a metal, yeah. But however, in strong magnetic field, so the electronic orbits get confined to these circular orbits, which are called Landau levels, and so the material gets actually, so this two-dimensional sheet, metallic sheet, gets insulated. However, as soon as these circuits, so the orbits, so they touch the interface between this two-dimensional gas, electronic gas, and say vacuum, so they start to form these chiral orbits, chiral currents, which run along the edges of this two-dimensional electronic gas. So this is a very interesting phenomenon which was discovered and studied in quite detail. So that means the bulk, or so to say the surface, is insulating in strong magnetic field, but the edges are conducting. So a similar situation is expected to be in the topological insulator, but for that one doesn't need even a strong magnetic field. So one has in this topological insulator the quantum spill Hall state where the currents, now which are spin polarized, also run on the edges. So, and then one expects that if one applies a magnetic field, one can make this surface a small magnetic field, one can make this surface insulating, but there still be conducting channels at the edges. And this is because, well, if one applies a magnetic field, one breaks the time reversal symmetry, and that, as a result, so there is a gap in the direct cone, and if the Fermi energy is in the middle of the gap, so the surface is getting insulated. But again, due to the topological properties of these electronic states at the surface, there should be a spin polarized current running on the edges. So indeed, well, so this magnetic topological insulator could be realized in different ways, and so there is a concept, different concept approaches to do that. So ideally, one would like to have a ferromagnet with a spontaneous magnetization which has an easy axis pointing out of the plane. In this case, if the electronic structure of material is topological and non-trivial, one immediately have these edge currents, spin polarized currents, because of the two gap surface, the gapping of the Dirac cones and the opposite sides of the surfaces. Experimentally, well, so far, there are different approaches how to realize that. One would be just simply to dope so the non-magnetic topological insulator like bismuth selenide or bismuth telluride with something magnetic like chromium ions. So the chromium spins, they order magnetically, and they generate so the out-of-plane magnetization. Or one can make a heterostructure with a non-magnetic topological insulator topped with, say, topological insulator doped with magnetic impurities. In both cases, so that it was really strictly experimentally confirmed that this is a magnetic topological insulator showing the quantum anomalous Hall effect, which is visible very clearly. So, for instance, in the quantized Hall resistance, which is quantized just in fraction of the fundamental units. So this is a Max Planck constant over the square of the electron charge. And this jumps, so the longitudinal resistance, as expected, its diverges getting to infinity. So this longitudinal resistance is telling us so that this material is insulating on the surface. So the same was made also for this doped magnetically doped topological insulator, so that the concept was proven. The only problem with this concept, not with the concept, but with the realization, so that all these magnetic dopings introduces inhomogeneities. Therefore, the scattering process take over, and these quantized states are visible only at very low temperatures of a few millikelvin. Now, another route turns to be very promising. So to create a material which is intrinsically magnetic, so that means so that the magnetic units are not somehow stochastically distributed in the material looking as magnetic scattering center, but form regular magnetic lattices. And the idea was that, well, one can start with this already known non-magnetic topological insulator, bismuth telluride, and introduce an additional double layer inside of it, manganese telluride layer. So manganese in 2+ oxidation state, it has half-full D shell, very large spin moment of 5-half. And indeed, so the material which shows this, this structure is the family of this manganese bismuth telluride, bismuth 2 telluride, and family. Actually, so the first representative of this family, manganese bismuth 2 tellur 4, for short 1, 2, 4, is made of these septuple layers. So that means these quintuple layers of bismuth telluride with with a double layer of manganese telluride. And so they are spaced along the C direction and are coupled only by weak van der Waals forces. So this is it's a magnetic van der Waals compound. The next member of this family is manganese 4 tellur 7, 147. And it differs from this one, only that one inserts one non-magnetic original quintuple layer bismuth telluride in between the magnetic units. So, in this way. Now, it was found so that this material orders magnetically, and of course magnetism is related to the manganese to 1 to 4 building block, because this one is non-magnetic, and so the spins of manganese, so they build up total magnetization, and this magnetization is in the neighboring layers coupled antiferromagnetically, so it's in the bulk, it's an antiferromagnetic insulator. Now, if one looks on the static magnetic properties of this compound, they're quite usual, so nothing special. One measures a temperature dependence of the magnetic susceptibility. One observes a peak at a temperature of 24 Kelvin. This is for 1,2,4 compound. And the susceptibility drops down at low temperatures, indicating so that it's antiferromagnetic phase transition. So now if one measures the magnetization as a function of field in the magnetically ordered state, one sees so that the magnetization is very small at small fields because it's a collinear antiferromagnet, but it has a step-like increase at a certain field, which is called the spin flop field, where it's the field at which these two sublattices they flop, and now the magnetization of the sample is increased. A bit more complex situation takes place in 1,4,7. Again, somehow it. Okay, now. So, well, if one looks on the static magnetic susceptibility as a function of temperature, it also shows a peak at a temperature of about 13 Kelvin, indicating a transition to the antiferromagnetic order state. But at smaller temperatures, there is kind of increase of the magnetization, suggesting that it's kind of a metamagnetic state, and with the hysteresis behavior of the magnetization. Actually, so this is an antiferromagnet, not a desired ferromagnet, but an antiferromagnet. How it could be that it could show some topological properties, and there was one pioneering work about 11 years ago on the prediction of the possibility that in certain materials, in the antiferromagnetic materials with a certain band structure, topological insulator state can be realized. So on the one hand, so that, of course, the magnetic order breaks time inversion symmetry, and also so this building up of this of the sublattices, they also breaks the primitive lattice translation symmetry. But in the case if the combination of both, it still preserves the time inversion symmetry. So then on the antiferromagnetic surfaces of this compound, so there can be ungapped Dirac cones. And on the ferromagnetic surface, they could be Dirac cones but gapped. So actually, this is what one would like to have. And that was really very nice, first of all, theoretical prediction in the group of Evgeny Chulkov, where so the main player was Mikhail Otrokov, who predicted so that in this manganese bismuth tellure 2,4, indeed, so this non-trivial topological electronic structure on the surface can be realized. So these are surface Dirac cones, and they exhibit a relatively small gap of about 88 millielectron volts, about 90 electron volts in the magnetically ordered state. So actually, so Mikhail will give an invited talk on Saturday in the afternoon session. I think that he will provide much more insights on the recent theoretical developments in the field of magnetic topological insulators. So you're invited to visit this talk. So in this our great collaboration of people, so then we of course looked for experimental evidence for this prediction, and indeed it was found in the ARPES experiments. So there were found these Dirac cones at the surface state which are gapped, and the gap was about 70 millielectron volts, very close to the theoretical prediction. Interestingly, although the intensity of these Dirac cones, it drops significantly by approaching the ordering temperature from below. So that means where the magnetic order is suppressed, one would expect so that this gap would completely disappear in the paramagnetic state, but it does not. It still shows some remainings of the gap with a bit field space, but kind of pseudo gap is still present at temperatures much more higher than Tn. So that was very unusual and unexpected behavior, which needs some explanation. So that this material 1,2,4 is indeed a topological magnetic insulator, but was ultimately confirmed also by measurement with anomalous quantum spin Hall effect. by Dan Kataev. It was published quite recently. So they measured it on a thin flake, or a few layer flake of this, of the single crystal, and then indeed, so they observed these quantized jumps in the transverse Hall resistance and the divergence in the longitudinal resistance, proving so that this is a magnetic topological insulator. So now similar results were obtained on 147, which contains in addition one non-magnetic interlayer. And so in the ARPAS experiment, so again, so indications of the surface Dirac cones were found by our group, but also by other groups. So the surface states are evident as well in this material. So, and then actually, so we wanted to have a bit more insight into the magnetism of this material by measuring electron spin resonance spectroscopy on these systems. And actually, so just to recall, so the basic principle of electron spin resonance spectroscopy is rather simple. It's based on the Zeeman effect. So an electron spin system is exposed to external magnetic field, so the spin levels are split due to the Zeeman effect. If one shines electromagnetic radiation with the energy, which exactly fits into the gap between this split state, so this energy will be absorbed, causing the resonant absorption peak, which is called electron spin resonance peak. And actually, in the classical description, so that simply means that the spins in the electronic spins in the spin ensemble, when exposed to the external field, so they start to process about this field with a frequency which is called Laramov frequency, and if the if the microwave radiation, so the magnetic component of this microwave radiation, electromagnetic radiation, is applied perpendicular to the external field and it has the same frequency, oscillation frequency, as the precession frequency of the spin will be tilted out of the z direction, will tilt to the xy plane. This causes the absorption, and there they will dephase due to different kind of relaxation processes, due to electron spin fluctuations, and that actually what can be observed in experiment. So usually, with this technique, one can probe in a paramagnet, so the electron spin dynamic, exchange interactions, spin correlations, and very importantly, the ordered magnet, one also measures spin wave excitation, so the uniform spin excitation of the sublattices at the Q0 wave vector. So now, before we started our experiment, so we wanted just to understand what we want to learn from that. And actually, the two important questions which arose to us were, first one, so let us quantify the magnetic anisotropy in this material, because it's essentially very important for the occurrence of a magnetic topological insulator. For that, we can measure spin waves and analyze them within the spin wave theory, and to determine all parameters of the magnetic anisotropy of this compound. The other important question related to the persistence of the Dirac gap, in the Dirac cones, even above Tn, is the dynamic and relaxation of manganese spins. If there is something special which could cause this unusual persistence of the gap in the disordered state. And actually, first we started with 147, which showed a very simple excitation spectrum. So it's just in the magnetically ordered state, it's just a single line which has a linear dispersion in the magnetic field. So this is a frequency, says energy, so 250 gigahertz, approximately 1 milli-electron volt. So one sees this linear dispersion, one turns the field in plane, and simply this resonant branch shifts to lower energy. And if one approximates this both to the zero field, one sees some finite frequency offset, meaning there is a finite energy required to excite a spin wave. So this is the so-called magnetic anisotropy gap. So as soon as we heat the sample above the ordering temperature, then the branches, they come closer together, they don't have a gap anymore, and this is a conventional paramagnetic resonant branch where the difference in the slope is given by the difference in the G factors. So we could analyze very easily these excitations in terms of the spin wave theory, and then we obtain quantitatively, the magnetic anisotropy energy. It's a number, minus about 0.2 milli-electron volts susceptible layers, per magnetic layer. Actually, so it's some numbers, so why should it be so important? One important thing that we can justify, so that's indeed is a minus sign, that means so this is out of plane anisotropy, so that means the magnetization indeed should stay, prefers to stay out of the plane, which is needed to make a gap at the Dirac cols. But then, so that means it stabilizes, so this out-of-plane ferromagnetic magnetization. But the next question, what happens, so if we just reduce the distance between these two magnetic layers? For that, we can simply take out this quantipole layer, so that which is non-magnetic, and then, of course, the distance between these magnetic layers would be shorter, and the antiferromagnetic interaction between the sublattices would be expected to be stronger. And indeed, so in this material 1 to 4, which doesn't contain non-magnetic units, we find an entirely different excitation spectrum in the magnetic order state. So it's not a single line, so it's a many resonant line which dispersed different in the magnetic field. One mode increases in energy, the other decreases, so they collapse, and then it forms so another branch which non-linear field dependence. So now this is what we measured for the out-of-plane direction of the external field, for the in-plane, and, well, actually we can also understand what's going on here, at least qualitatively. So this would be a two typical excitation mode for the two sublattices of the collinear antiferromagnet. One precesses in phase, the other out of phase. One increases in energy, the other decreases. Then at a certain spin flop field, so they flop into the perpendicular direction, and now they all precess in phase, and finally, so they reach the forced ferromagnetic state, forced by an external magnetic field, like this. Actually, so when we change the orientation of the field from the out of plane to in plane, so then we have completely different excitation spectrum. These are two modes, this one and the other one which we observed. Well, one could say, okay, so this is a complex diagram, but what's special in this? A special thing for experts, and I will try to give you a feeling why it is if one compares to the paramagnetic resonant line, which is like here. So this is what would be entirely due to the Zeeman effect. One sees so that, well, somehow these branches, the in-plane and out-of-plane branch, so they cross each other, but also the in-plane branch crosses the paramagnetic line. And this is extremely unusual because in a conventional collinear antiferromagnet, so this in-plane mode, it should approach so this paramagnetic line from above, but never cross it, but approach it asymptotically. So the other mode, the red one, for the out-of-plane orientation, it also should approach so the paramagnetic line at higher field asymptotically, but never cross it. But here we observe a crossover field, which is quite turns out to be very specific for this 1,2,4 compound. So, and actually, so, well, if we just consider the high field region, so above the crossover field, so the modes are exactly the same which we observe for the 1,4,7 material. So these are just sketched by these dashed lines. So this is the ferromagnetic modes which we observe in 1,4,7. And actually, so these antiferromagnetic modes at low fields, they turns into ferromagnetic modes at higher fields, which is quite unusual. So now, what is the physical consequence or the physically relevant conclusion from this observation? We could fit all of these antiferromagnetic modes again with the spin wave theory, and we could obtain so the exchange interaction between the layers, between these magnetic units. It's also negative antiferromagnetic. It's about 0.7 millielectron volt. And also we obtain the energy of an individual magnetic unit, the susceptible layers. And it turns out to be negative and 0.2 millielectron volts. And now let's compare it with the result of the 1,4,7 compound. There we obtained very similar values, although the structure is not completely, but different. So that means so this comparison and comparative study of this 1,4,7 and 1,2,4 suggests so that the magnetic units of this family of magnetic topological insulators is inherently easy access to dimensional ferromagnet. So the details of the structure is not so important. Either it's separated by 1 or 2 or 3 non-magnetic layers, so the magnetism is confined to these individual layers, and it's stable, and it is out of plane. So that is quite important for the realization of the surface gap in the electronic states, which is observed experimentally. And now I shortly will comment on our results on the dynamics and relaxation of manganese spins above the ordering temperature in the paramagnetic state, where we also came to very interesting conclusions. Now, actually, so we measured, say, electron spin resonance in both materials above ordering temperature, and you see, so this, in this case, so this is the derivative of the absorption signal. So you see, so the line, it shifts a bit, so then it broadens, and the resonant field has the following temperature dependence. As soon as we leave the magnetically ordered state, where there is a strong anisotropy of the resonant field, so regarding the orientation of the external magnetic field, and we have some region where this short-range correlation, very typical to a low-dimensional magnets, a two-dimensional magnet, are present, but above a certain temperature, so the resonant field is truly paramagnetic, isotropic, and the same is true for both compounds. So now, but if we enter the paramagnetic regime and look at the temperature dependence of the line width, which is the measure of the spin fluctuation, of the spin relaxation of manganese spins, we see a linear behavior in both cases, but in the case of 1 to 4, a more concentrated magnet, so we see that this, the slope of this linear dependencies is very anisotropic, and here it's very isotropic. This is also quite unusual. Just to recall, so actually, so the line width is given by the fluctuating field acting on the electronic spins. They could be generated by from other degrees of freedom. And we also should recall that the materials which we study, so they're not entirely bulk insulators. They were n-doped, so that they have some bulk electrons. And the manganese spins, they relax on these bulk conduction electrons. And this is a very specific kind of spin relaxation, which is called Corringer relaxation process. So the spin flip on the conduction electron, which is linear in temperature, and its strength is determined by the density of electronic state and the coupling between the localized and itinerant state in the bulk. So, and now, well, to understand, so why in one case we have a very anisotropic behavior and the other one is not, so then the theory helped us a lot. So that was a band structure calculation where our theory colleagues also calculated the band structure with respect to the direction of the localized manganese spins. And so here, a very interesting result was observed. So, for instance, so this is an integrated density of states for out-of-plane and in-plane orientation of the manganese spin, and one sees a substantial difference in the 1 to 4 materials, whereas in the 1 to 7 materials, so there's practically no difference, no dependent on the manganese spin direction. And this anisotropy, so it causes respectively so the anisotropy of the fluctuation rates of the manganese spins due to the anisotropic relaxation on conduction electrons. And therefore one can just make a very simple picture of the bulk manganese spins fluctuating anisotropically in the paramagnetic state, so they generate some kind of instantaneous out-of-plane magnetization, because so the fluctuation along the c-axis is much smaller than in the plane, as is shown by different slopes of these relaxation curves. And that could be actually important, the reason for the observation of the non-vanishing gap or pseudo-gap in the Dirac cone also above the ordering temperature, because, well, considering the time scale of the ARPES experiments, so this fluctuation could be quasi-static. So, and also the theory predicts that there should be a very strong concentration dependence on the anisotropy of the manganese fluctuations on the concentration of the bulk charge carriers. And indeed, so that could explain so the difference in our observation 1 to 4 and 1 to 7 compounds, because we had samples with different concentration of charge carriers. So it was much smaller in 1 to 4, where the theory predicts a strong anisotropy, and it was much higher in 1 to 7, where the theory predicts in this regime practically isotropic isotropic behavior.
10 more minutes.
Oh yes, so I'm my last slide. So actually, so this our first experimental observation and also this theory predictions suggest that anisotropy of the manganese spin dynamics and its impact on the surface states could be tuned by controlled and tuned by the charge doping. So this brings me to my conclusions. So in my talk, so I think so I'll introduce you, give a flavor of this new manganese bismuth telluride family of magnetic topological insulator, which provides a fascinating platform to investigate the interaction between two apparently conflict states of ordered matters, so the magnetic order and the electronic order. And what we could learn so far, from our electron spin resonance experiment, so that indeed in the ground state, so the magnetic ground state, the spin waves are very different in these two materials. However, if we extract the specific properties of the magnetic building unit, so the manganese bismuth 2 tellur 4 layer, it turns out so that it really has an inherent property of easy access two-dimensional ferromagnet in both cases, and we can generalize it to other members of this family, which is essential for the realization of this magnetic topological insulator. Another interesting observation, so that we found a strong anisotropy of the manganese spin fluctuations in the disordered state, which help to maintain kind of dynamic gap on the surface cones, even in the absence of the magnetic order, which could explain our ARPES experiments. So finally, there is a theoretical suggestion from our colleagues, so that this dynamic spin anisotropy can be controlled by the charge doping, but this needs more experimental clarification, which now is an ongoing project. So with this, I would like to thank you for your attention.
Professor Kataev, I have a question. When you compare your results with experimental data, is there any size dependence of the properties in topological insulators?
Which dependence?
Size of the measured samples.
Yeah. So these are not our own experiments, but they're experiments which I mentioned to you. So this, not to all of us. So this measurements of the quantum Hall effect in the thin layers of, in the flakes of 1 to 4, manganese bismuth. And indeed, so they observed that this effect increases with decreasing the number of layers. And so at least in this dimension, yeah. And that is clear because in the bulk, so you have many magnetic layers which are antiferromagnetically coupled. But as soon as you reduce the number of the layers, so the probability that you find a flake which has an odd number of magnetic layers is high, and therefore in this sample you could see really very nice.
So these are very thin samples of nanometers, something like that.
Yes.
Understand.
Yeah.
Now, another question is, how do you control the distance between the magnetic layers? Is it possible experimentally, or do you just assume that?
No, we control that by chemical synthesis.
Okay.
So let me come back. So here, yeah. So okay, so somehow we cannot make one material either containing non-magnetic layer or not containing non-magnetic layer. We have to synthesize two of them. So that means that we have, say, this manganese bismuth tellur 4, which contains only magnetic layers, but we can synthesize another material which contains also non-magnetic layers in between. So this automatically leads to a change in the distance between these two layers, and in this way we can control the magnetic structure.
Understand. Thank you very much.
Yeah.
Any questions from Salon? Yes, please.
At the beginning, you mentioned XCMD, magnetic dichroism.
Yes.
Which results did you obtain with magnetic dichroism?
Oh, yes. So that was a very important experiment. That's a very good question. Because, well, the gap is on the surface. the magnetism is in the bulk. The question is if this magnetism, so the ferromagnetic magnetization, is present at the surface of this sample. This is not that obvious. It could be some surface defects or degradation or whatever, which suppress the magnetization of the surface layer. For that, we made this XMCD experiment, so X-ray magnetic circular dichroism, which has a very small penetration depth, and we'll definitely see magnetic signals in the samples which show this gap in the Dirac cones.
Any more questions?
This
Yes,
one.
please.
I have just a simple question. Can we classify this family of materials as frustrated magnets?
What do you mean by frustrated?
Frustrated magnet is it itself is something like a triangle, and
No, this I know, but no, yeah, okay, clear. So I would say, so in this sense, so these materials are not frustrated. Not frustrated. So because, well, actually, so what is established now very well is that this two-dimensional magnetic layer is actually a ferromagnetic layer with all moments of manganese ions parallel. So they're all happy, they're not frustrated. And there is also a stronger or a weaker interlayer interaction, which is antiferromagnetic. So that means the sublattices are in zero magnetic field, so they're antiparallel, collinear, and there are no any conflict of interest, so to say, which is usually the case in the frustrated magnets.
Any more questions? No. Any questions from the Zoom? No? Okay. Then, if I forget to present this
Oh, thank you very much.
Thank you.